Imagine we want our robot to catch a ball using an RGB camera. One way to accomplish this task is to use reinforcement learning. We conduct a number of trials in our lab, iterate our policy, and eventually the robot learns to catch a ball. However, when we move our robot out of the lab and into a production environment, the robot starts missing the ball again because of irrelevant environmental factors like a change to the wall color. This is a common problem encountered in reinforcement learning when working with high-dimensional sensors. The learned policy overfits to the training environment and produces an unnecessarily tight coupling between the robot's sensors and actions, which causes the robot to perform poorly in new environments. In order to learn robust policies using standard methods, data needs to be sampled from a large amount of possible operating environments, which is impractical. Instead, we propose that robots should be learning task-driven policies that only respond to changes in task-relevant variables that are persistent across operating environments. Therefore, our robot should be able to learn a robust policy within the lab. One example of such a policy is what is known as the gaze heuristic in cognitive psychology. In order to catch the ball, the robot only needs to monitor the gaze angle, which is the angle between the ball and the ground plane at the robot's location. If the robot moves such that this angle remains constant, the robot will arrive at a position to catch the ball. This policy depends only on a single task-relevant variable, the gaze angle, and works equally well in the lab with a brick wall backdrop or outside with a blue sky. Moreover, it automatically corrects for disturbances like wind gusts and is therefore robust. The goal of this work is to automatically learn robust task-driven policies like the gaze heuristic for whatever task the robot is trying to accomplish. To do so, we restrict our policy to depend on a set of minimum information task-relevant variables. These are found by minimizing the mutual information between the task-relevant variables and the system state subject to a constraint on the expected cost during learning. The mutual information is a measure of statistical dependence, so minimizing it yields a set of task-relevant variables that depend as little on the system state as possible. In other words, the task-relevant variables create an information bottleneck between the full state of the system and control actions, thereby filtering out task-irrelevant information. The resulting task-driven policy is thus minimally impacted by irrelevant changes in the robot's environment. In order to minimize this objective, we use a policy gradient style algorithm that seeks to solve this optimization problem in a data-driven manner. To demonstrate the efficacy of this approach, we apply our algorithm to 3 examples. First, we consider what is known as the lava problem. Here, the robot must navigate to a goal position on the line without falling into the lava. When given access to the full state of the system, the robot can simply move directly to the goal, and this policy is learned by standard policy gradient methods. However, this policy breaks down when the robot only has a noisy estimate of the state. It may believe, for example, it is to the left of the goal when it is actually to the right of the goal, and take an action that causes it to fall into the lava. However, our algorithm learns an open-loop policy that is invariant to increases in estimation noise. The robot accelerates left with enough force that it bumps into the wall, no matter its initial sensor reading. This localizes the robot and allows it to move directly to the goal without error. Next, we apply our algorithm to a grasping example where the robot's task is to lift a mug using a depth image. During training, the robot is only exposed to a limited set of mug positions and rotations. When evaluated with the full set of possible rotations, our policy outperforms traditional policy gradient methods. This is due to the fact that the mug is almost symmetrical, and that the orientation of the mug is largely irrelevant to the task of lifting it. When the set of possible translations is expanded, both policies degrade similarly, since position within the camera frame is task relevant, especially when only a fraction of the mug lies within the frame. Finally, we evaluate our policy on the ball catching example described earlier. As can be seen in this video, while both policies perform well on the red brick training environment, the performance of policy gradient begins to fail when we switch to a gray backdrop. We repeated this experiment with a number of different backgrounds and found our policy outperforms standard policy gradient methods on all but one background, and this background is red in color like the training environment. These results demonstrate the task-driven robustness of our policy. Thank you for listening, and please come by our virtual poster session if you have any questions.